So once again, I'm here with yet another topic on this bipolar junction transistors or BJTs. So in this lecture, I'll be covering two important points, that is common collector configuration of BJT and the Ebers Moll model of BJT. So coming to the first point, that is the common collector configuration of BJT. This common collector configuration, it is represented by this figure, where the load resistance, it is this load resistance RL, it is connected between the emitter and the ground rather than the collector and the ground. Okay, so mainly it is used, this configuration, it is mainly used for impedance matching, since it has high input impedance and low output impedance. So this circuit is similar to the common emitter configuration from the design point of view, and hence there is no need for a set of common collector characteristics to choose the parameters of the amplifiers, just like in common emitter configuration. So for all the practical purposes, the output characteristics of common collector configuration are same or similar as that for the common emitter configuration. So for the common collector configuration, the output characteristics are simply the curve, or you can say a plot of IE versus VCE for different range of base currents, that is IB. The input current is therefore the same for both the two types of configurations, that is CE as well as CC configuration. The horizontal voltage axis for common collector configuration is obtained by simply changing the sign of the collector to the emitter voltage of the common emitter characteristics. Now we know that since IC, that is the collector current, it is directly proportional to the emitter current, and it is related by this equation, that is IC equals to alpha into IE, and alpha is nearly equal to 1. So there will not be any remarkable change in the vertical axis characteristics as compared to the common emitter characteristics. So this table basically, it represents the various typical junction voltages, and these junction voltages are for NPN transistors. They are taken at 25 degrees Celsius, given in volts. So you can see these two types of transistors, they are mainly available, and these two semiconductors are there is silicon and germanium, and what are the voltages, junction voltages in different modes of operation, that is cut off when VBE is cut in, then VBE is in active mode, then VB in saturation mode, then VC is in saturation mode. So this table basically, it gives you the values of the junction voltages for a NPN transistor. Now for a PNP transistor, the sign of all the entries are reversed. Okay. Now it should be remembered, and we have already discussed earlier also, that for the transistor to be in active region, the collector current, it should be equal to your beta into IB. If we neglect the value of ICO, that is reverse saturation current for collector, and in the saturation region, the base current, it should be slightly greater than or equal to IC upon beta. Now coming to the Ebers Moll model of a BJT, we have already studied through equation that shows the dependence of current in a transistor upon the junction voltages, and that is given by this equation, that is IC equals to minus alpha IE minus ICO into e raised to power of VC upon VT minus 1. So for a physical transistor, the emitter and the collector junctions are quite alike. You know this, they are basically symmetrical, except with a little difference that in the electrical conductivities of these layers are there, and that is because of the presence of the different doping levels. So theoretically, one may think of a transistor in an inverted mode, that is the role of emitter junction and the collector junctions when interchanged. Now if we take such an arrangement, it might not give as effective results from the normal mode of operation. So in order to represent the normal mode of operation and the inverted mode of operation, these two equations are there. So we write two current equations, one for the normal mode of operation, that is by replacing alpha by alpha n here. There is the current gain in normal operation, and the other for inverted mode of operation by replacing alpha by alpha I, which is for the current in the inverted mode of operation. So here in the previous equation we have replaced alpha by alpha n for normal operation and alpha by alpha I for the inverted operation. So in the inverted mode of operation, IE has been replaced by IC and vice versa, VC by VE and ICO by IEO, as the role of the emitter junction and the collector junctions, they are interchanged. So IEO is the emitter junction reverse saturation current in this case in the inverted operation. Now these two equations, they are defined using this figure for a PNP transistor. They can be represented by this circuit, and there can be these equations can be derived out from this circuit, and this circuit is mainly for a PNP transistor. Okay, so for either transistor, that is either for a PNP or a NPN transistor, a positive value of current means that there is a positive charge flow into the junction, and a positive VE or VC, it represents that the corresponding junction is in forward bias. Now if a resistance RBB dash, which is also known as the base spreading resistance, is supposed to be connected between a point on the active base region B dash and the base terminal B, as shown in the figure in the previous slide, the base spreading resistance is basically the DC ohmic resistance of the semiconductor material between any 2 points. Now the voltage drop across the collector to base terminal, it differs from VC by the potential drop across the base spreading resistance RBB dash, and which is represented by this equation, that is VCB equals to VC minus IB into RBB dash. Now these two scientists, that is J.J. Ebers and J.L. Moll of Bell Telephone Industries, in 1954, they proposed a very simple transistor model based on the two equations, that is the equation for normal mode of operation and for the inverted mode of operation. So these two these two figures, they represent the Ebers-Moll model, and they are respectively for a PNP transistor and for a NPN transistor. Okay. So this model, it basically contains two diodes which are placed back to back with a reverse saturation current minus ICO and minus IEO, and the two dependent current sources shunting these diodes. Now for NPN transistor, the direction of the diodes are reversed, and the corresponding equation for NPN transistor will be same as given in the equation on the previous slide, that is slide number 9, with the difference that VE will be replaced by minus VE and VC will be replaced by minus VC, as VE and VC, they make the diodes in the reverse bias condition. Now the model which is developed here in this you can say section or in this lecture, they are characterized by 4 parameters. Okay, the equation contains 4 parameters, that is alpha n, alpha I, ICO and IEO. But these parameters, they are not independent actually, they are simply related by this equation, that is IN into IEO equals to alpha I into ICO. Now basically this it represents the reciprocity condition. This reciprocity conditions, it shows that at least 3 parameters of these 4 parameters, they are sufficient enough to find the characteristics, or you can say to characterize the static VI relationship of a transistor. If the dependent sources from the figures depicting these models, they are eliminated, then the transistors may be represented simply by 2 diodes which can be placed back to back. Now this is possible if alpha n and alpha I are taken to be 0. Now the current gain alpha will be 0 if the base width is made much larger. Physically, how this alpha can be made 0? So this current gain alpha, it will be 0 if the base width is made much larger than the diffusion length of the injected minority charge carriers in the base region. All the minority carriers in that case will recombine in the base and none will survive to reach the collector. So what can we conclude? Now under this condition, basically the transistor action it ceases. Okay, so therefore we can conclude that it is almost impossible to construct a transistor by simply connecting two diodes in back-to-back connections. So with this, I finished these two topics, that is common collector configuration and Ebers MOS model. For any doubts, you are welcome to contact me on the WhatsApp group or in the Google Classroom. Thanks for listening.